Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so this is the continuation to my previous video. So we discuss about frame with side sway analysis. Now is under step 3B. So for step number 3, actually we will do side sway frame. We will do side sway frame. For table number 2, we are going to determine the end moment. And we actually refers to diagram D. So in diagram D, so we actually introduce another diagram, which is subjected to R prime. Since the frame is moving towards right direction, so R prime also we put in the right direction. Okay, and then at fixed support at A and fixed support at D. So there are three unknown reaction, and we label the vertical and horizontal reaction at A as V prime 1 and H prime 1 respectively, and also M prime AB. And then at D, there are horizontal and vertical reaction. H prime 2 and V prime 2, as well as M prime DC. Okay, so since this is side sway frame due to R prime, so we actually will calculate M prime based on the FEM assumption. And in my previous video, we have discussed about step 3A. Step 3A basically is the FEM assumption due to side sway. So where we have to identify the delta 1 prime, delta 2 prime, and delta 3 prime for each member. And for member number 1, member AB, we use delta 1 prime. For beam, we use delta 2 prime, and for CD, member CD, we use delta 3 prime. So for the FEM calculation, so we use delta 1 prime, delta 2 prime, and delta 3 prime in the formula to calculate FEM. So we will choose one member to assume the FEM. So this is just revision. Okay, so we have like this. So the FEM that we assume is only one. We choose negative 100. We assume negative 100 for member AB. So due to this value negative 100, we have to find the value for member BC and for member CD, which is proportional. So we will calculate based on the formula. The formula is 6EI delta over L squared. Okay, and we get the value, the FEM for member BC equal to positive 83.333. The positive means for beam it rotate clockwise, and for FEM for CD it rotates counterclockwise, and the value is negative 25. The detailed calculation about this assumption have been explained in my previous video. Okay, we move to table number 2. Table number 2 is the moment distribution table. As usual, the table must have distribution factor, which we calculate based on stiffness, member stiffness, and joint stiffness. Okay, so the detailed explanation about this have been discussed as well for in my previous video under step number one video. Okay, so and FEM that we have just calculated based on assumption, the negative 100, positive 83.33, and negative 25, we put in the FEM for each end moment for ABBA. And please remember for FEM due to side sway, FEM due to side sway for AB and BA, because the behavior is the same, AB and BA. So we have to have the same sign. Okay, the behavior, so we can look at this. So this is the behavior. So in order to for the beam, for the column, so this is the column actually after side sway, the column after side sway. So original is AB, original is AB, and due to side sway, the column move like this, move to the right direction, and the moment the FEM actually will counter back. So the counter back moment is actually occur in counterclockwise direction. So that is why the value is negative 100. The value is negative 100 because we want to push back the new position of beam, this beam, to its original position. So we have to apply the moment counterclockwise. So that is why it is negative. So we put and both AB and BA have same sign, so when we have like this, and then we apply moment, apply in same direction, that is why we get negative, for negative 100 for AB, and negative 100 for BA. Okay, for member BC, the value is positive 83.33. So the value is 83.33. So this is the value, 83.33. And one is for BC, another one is for CB. For BC and for CB, are both are positive. So why it is positive? Because of the behavior. Because of the behavior. So look at the behavior of beam after side sway. So due to side sway, the beam, the original position is horizontal. So this is original position, the horizontal uh, position. After side sway, it move to this position after side sway. So the beam, the moment, the fixed end moment for beam will push back the new beam, the new position of beam to its original position, and we have to apply the apply moment clockwise. We have to apply moment clockwise. So that is why, as we can see, this is positive, this is also positive. So this positive 83.333 we put into the distribution table, one for BC and one for one for CB, one for BC, one for CB. Okay, next is member CD. So let's look at the diagram for member CD. CD is a vertical member column. Column CD is a vertical member, and due to side sway, the column move to new position like this, the new position. Okay, new position. And due to that, so the fixed end moment will actually counter back, the new position of beam to its original position. We push counterclockwise both side. So the value for CD and DC, both are negative value because it has same sign, and the value is 25. So we put the value negative 25, negative 25. So please remember, when we analyze FEM due to side sway or due to delta, we must have same sign for ABBA, CBBC, CDDC. Okay, so for FEM due to external loading, we get one negative, one positive because of the behavior as well. Okay, and after that, so this is the FEM, the FEM. So from this FEM, remember FEM is the first the member and moment in the table, and the moment that we distribute in the table is not member and moment but joint moment, so we have to distribute joint moment. So what is actually occur is, okay, so we have to find joint moment. So we have joint A, joint B, joint C, and joint D. So for joint A, since the distribution factor is 0, so okay we leave like that. So we focus on joint B and joint C. D also fixed. Okay, joint B and joint C, we have to find the total moment or joint moment. Joint moment for B is actually look like this. Joint moment at B. So joint moment at B, we get like this. Okay, I use the concept taken from BEAM. So the process is actually the fixed end moment. The fixed end moment from from BA is negative 100. BA is negative 100. So this is negative 100. And BC is 83.333. 83.333 is positive. Positive. Negative and positive. Negative, positive. Okay, this is 83.333. Okay, so the fixed end moment that we write in the table is actually this value. And it represents member and moment. Anyway, the moment that we distribute is not this, but we distribute joint moment. And joint moment is this and this, the joint moment. And joint moment is always opposite with member and moment. So the moment that we distribute is joint moment. So means that we will have, this is 100, this is 83.333. So joint moment at B is actually 100, we minus by 83.333. This is the joint moment. The joint moment. Okay. The joint moment. So we get positive value. We get positive value. So it is equal to 100 minus 83.333. So we get 16.667 for the joint moment. The joint moment. Then only we distribute. So when we distribute this 16.667, we distribute to BA and BC. For BA, the factor is 0.375, 0.375, and for BC, the factor is 0.625. 0.625. So this is actually what happened in the table. So it is 16.667 times 0.375. So we get 6.25, and another one is 16.667 times 0.625. So we get 10.417. So this is the value in the table, 6.25 and 10.417. 6.25 and 10.417. So to calculate whether it is correct or not, we just need to plus all this 1, 2, 3, 4, and whenever we so it should get 0. So by total these four values we should get 0, representing MB is equal to 0. Okay. Okay, even though this is beam, but the process is actually the same. So frame we have like this lah. So this is rigid joint B. This is what is actually occur B. So the moment 83 is this one, and 100 is this one. This is 100. This is 83.333. The joint moment refers to opposite this, and opposite this. So this is actually the joint moment representing by this. Okay. So that is for joint B. That is for joint B. Is for joint B. So we continue to calculate the value for joint C. Okay. So we continue. We continue at joint C. At joint C, we want to find the total moment at joint C. Total moment at joint C means we have to combine this 83.333 and negative 25. But we always remember that these two value is representing the member and moment, not joint moment, because joint moment is opposite, and it is actually look like this. So we have, this is C. We have 83. Here is 83.333, and we have negative 25. 25. So this is actually the fixed end moment. The fixed end moment representing the first member end moment in the table. So what is actually occurred is we have to calculate the joint moment which is opposite. So this one is 83.333 and 25. So we will distribute this joint moment. So for the joint moment at C is equal to negative 83.333 plus 25. So this one we get negative 83.333 plus 25. So we get negative 58.333. And this joint moment, negative 58.333, we have to distribute to CB and CD. So for CB, CD, so we use 58.333 times with the factor. The factor is 0.75. 0.75, and another one is 58.333 times 0.25. Okay, it is negative. So 58.333 times 0.75, we get 43.75, and 58.333 times 0.25, we get 14.583. Okay, 43.75 and 14.583. Okay, it is negative 43.75 and 14, negative 14.583, plus this 25, plus negative 25, plus 83.33, total we get 0. Represent MC is equal to 0 for joint equilibrium. Okay, so that is how we get distribution. So this is distribution. So for distribution, we change sign. We change sign because the moment that we distribute is joint moment, not member and moment. So we have to change from member and moment to joint moment first. And always remember, joint moment is opposite with member and moment. Then only we times with the distribution factor to distribute to BABC as well as CBCD. Okay, so this is the case where there is no applied moment subjected at node or at join. Actually, when for example, if in the question, for example, if in the question, let's say under the question we have another applied moment like this, 330, 30. So where we should put this 30? So this 30 actually we do not put into into CB or CD, but we actually plus with the joint moment. Then only we distribute, because I receive question regarding this. Okay, so after that, we move to carry over. Carry over. For the carry over actually we want to carry the value to opposite join, and carry over a factor. There are two value based on far end condition. So we have for end fixed and for end roller or pin, and internal always assume fixed as well. So for far end fixed and internal, we use 0.5 for the factor, and for end pin or roller we use 0 for the factor. So since in this example, so A and D are fixed in, and internal also fixed, so all factor we use here is 0.5. So that is why we can see that the value that we carry over, we divide by 2. Okay, so at this level carry over, we have to remain sign, do not change sign. We just times with the factor 0.5. So we get for AB we get 3.125, and then for BC we get negative 21.875. We get from negative 83, we get from negative 83.75. And then for CB is 5.208, we get from 10.417 times with 0.5. And for DC, we get negative 7.292, we get from negative 14.583. Okay, that is the process. We distribute moment and we carry over the moment. We carry over the moment. Then we have to repeat again. Repeat again distribution. So the process, as I explained here, the process under distribution level. So we repeat the process until 5 or 6 times distribution. Uh, 5 cycle, 6 cycle normally, and we have to stop at distribution. Stop at distribution. Do not stop at carryover. We have to stop at distribution. Whenever the moment reaches zero, we find 0.0. Actually, this value we can continue to distribute another cycle, but doesn't matter since the process will be the same. We assume that 1, 2, 3, 4, 5, 6. Okay, already 6 cycle, then we may stop the process. So once we stop the process, we have to total all the moment, start from fixed end moment. We have to plus all this. Okay, we have to plus all this, and we get the end moment m prime for member AB, and it is equal to negative 91.884. Okay, and then again we do the same for member for NBA. NBA, we total start from this negative 100 until 0.113. So total we get negative 83.655, negative 83.655 the total. And we continue to calculate this one for BC. And please take note that BA and BC means that it is representing MB, where MB is BA plus BC, MBA plus MBC. So that is why we will get negative and positive, the same value, but one negative, one positive. Okay, to represent MB is equal to 0. So we total for member CD and CB, and then we continue to calculate the end moment for CD, and last value is DC. Okay, so inside this we can see that, okay, these two value is one negative, one positive. Okay, MB, representing MB is equal to 0, and these two value is one positive, one negative, representing MC is equal to 0. Okay, and this is table number 2. So the moment in table number 2, the end moment in table number 2, we label as prime M prime. Okay, M prime. So this is actually what happened under step 3B. We calculate end moment due to side sway frame. Okay, so in the next video we will continue to calculate the R prime value. Okay, thank you very much. We will meet again in the next video.